now, like a regular
Yes,
presentation?
yes, it's okay. Please start.
Okay. So, hi everyone. I'm Socrates from Greece Team B or something. This is the now problem number 17, which is called Invisibility. So, our presentation consists of four main contents. That's the theoretical background, then the experimental setup, then the results of the experiment, and the conclusions we made. So, before I begin, maybe we should mention what a lenticular lens is in general. It is basically an array of lenses designed in a way that when they are viewed from different angles, different parts of the image underneath the lenses are shown. Uh, that's an image where you can see a narrow and a wide angle. So, if you take a closer look at the lenses, they basically consist of a front surface which has a spherical cross section, like right here, if you're able to see my cursor, and rear surface which is basically flat. So, before I move on with all the theoretical parameters, maybe we could mention two major uses of such lenses. First one is for autostereoscopic 3D displays. Like some of us have been in cinemas watching a 3D movie. You may have noticed that you need special glasses in order for the movie to have this 3D effect. Now, some TVs are using displays which, instead of those regular lenses you see in A, they use lenticular lenses like here in B, which give this 3D effect. Now, the other use is, of course, invisibility shields, the more fun one, because uh, um, objects with direction perpendicular to the one of the lenses, they seem to disappear like the legs of this man or this tool, but objects with direction similar to the one of the lenses, they seem to remain the same like the sticks and the lines. Now, let's continue. The main parameters we're going to use right now are R, firstly, which is the angle between the extreme ray and the normal ray, but at the point of where it exits the lens. P is the pitch or maybe the width of its lenticular lens. R stands for the radius of curvature of its lenticule, is the thickness of the whole lenticular lens, and H is basically the thickness of just the substrate, which is below the curved surface of the lens. And we also have N, which is the refractive index of the lens. Here in this image, you can take a better look at what this really mean. So we have R here, which is derived from this equation. This equation uses the P or pitch and takes the height of the substrate, which is shown right here. But A, in this case, can be measured from the second equation, which uses pitch and radius. And for the height of the substrate, we have this equation, h equals e minus f. And for the f, this height, we have the last equation. Uh, okay. So in order to measure the invisibility effect, we need to measure the intensity of light. So we have the intensity profile function, which is this one right here. We're talking basically about RGB pixel displays. So in this profile, you may notice that we're using some different parameters like W here, X, the F and FM or FO, and also the delta function, and also S. Now, to make it clear, because we're measuring light intensity, we have to divide it into green, blue, and light, and green, blue, and red light. So S takes a different value for its wavelength. As you see here, 0 is for red, 1 for blue, and 2 for green. And for FO, we're using this function, which uses X and W, and for FM, the second function. So now to make it clear, X is basically the position of the viewing plane. Um, and W is the width of its pixels. Now also F is the angle of the light which is emitted, and XS is the starting position of the subpixel. Here is the delta function, which also uses the G function and the gamma parameter. Gamma is generally a Broding parameter, which is the value we need for the whole function to work. Now I talked about the viewing plane. Basically, the viewing plane is the sensor we're going to use. I'm going to make it clear in the following slides. In this image, you can also see what this means. So here we have X and XS, which I said talk about the position of the viewing plate and the start position of the subpixel. Um, but you have to convert theta t and r to r and r in order for the image to make sense. Um, so for the experiment, we made two basic hypotheses. The first one says that if we increase the thickness of the substrate below the curved surface of the lens, which means the parameter 8, the invisibility effect will be lowered on the object. And the second hypothesis says that if we increase the distance between the base plane and the viewing plane, the invisibility effect on the object will also be lowered. Now, I have to make clear that, as I said, the viewing plane is a camera sensor, and the base plane is actually the rear surface of the lenticular lenses. So for the first hypothesis, we conducted an experiment. Um, okay, where we increase the thickness of the substrate, and as you see, as the thickness increases, the visibility decreases. So that means that basically the invisibility does increase instead of decrease, as we stated in the hypothesis. For the experiment, we used a 4K camera sensor, which recorded the outcomes of different thicknesses we used. The camera was also positioned always in a straight line from the object, and the distance was always 20 centimeters. Now we have the uh, equation for R that I have already showed, but we also have Beer's law, which says that A equals ELC. But here I should mention that A is a different thing. It's not this A. This one stands for observance. And what Beer's law says is that observance equals to the molar to uh, just a minute, attenuation coefficient, which is different for each material, talking about the lens. L is the optical path in which the light has to travel inside the lenses, and C is basically the speed of light. So we made a graph where you can see that as the thickness increases, the visibility exponentially decreases, and that can be seen because when you increase h, um, not only does r get a bigger value, but also the area in which the light has to travel gets bigger. So L, the optical path, gets also bigger, and more light is absorbed, so we have more invisibility effect. Now for the second hypothesis, we change the distance between the base plane and the viewing plane, as I said, in order for the